Yeah, also I would like to finish these talks on applications of piecewise deterministic Markov processes in risk theory and applications of Quasi-Monte Carlo integration by looking at two concrete or explicit applications of this technique. Yeah. Okay. Then yeah, also two applications. The first one is we look at this type of risk measure called the discounted penalty function. And we look at the problem for an reflected surplus process, where we need to use this type of coefficient smoothing we've seen in the context of piecewise deterministic Markov processes in the second talk. Yeah. And then a further application is a little bit to get correct initial values for stochastic optimization problems. Yeah, I've indicated this type of questions also in the second talk, and it relates a little bit to Feynman-Katz formulas, for which we are missing explicit boundary values. Okay, now let's start with the first problem. The idea is to use this type of Kramer-Lundberg or classical risk process. This means we are using a compound Poisson process, modeling cumulated claims, or not compound Poisson, we use some compound sum, random compound sum, for modeling cumulated or aggregated claim amounts up to time t. We have some premium income, but now not assumed to be non-constant. So we come back to this C, and we start with some initial capital. Yeah. Also for not doing classical, or using classical risk model, we use some renewal type counting process. Yeah. This means we have some interjump times WI, or the interjump times form an IIT sequence of positive random variables, and we use some distribution function FW for the moment for time. Yeah, this means that the time of the nth jump is the sum of the first n interjump times. Yeah, for the claims we assume an IIT sequence again of positive random variables, and yeah, claims and interjump times are assumed to be independent. So this is the classical Sparre-Anderson or renewal risk model setting. Yeah, but for the drift, we assume to have a drift function which is C2, and our idea is to mimic somehow a reflection of the process at the level A. Yeah, also the ideas we use a state space or as one component of the state space of this process, just the interval 0 to A. And the process may grow towards A, but cannot cross the level A. Yeah, so we would like to force the process to stay below A, but in a smooth way. Yeah. Okay, and some assumptions we will meet or we will use later. This means should be negative, such that the deterministic flow of the process in between jump times is concave, and then we ask for bounded derivatives, because we are using this later anyway, or we need to use this later. Okay, the idea somehow for this type of C, we could have used a constant parameter C, and then just switch everything off if the process hits the level A. This means that we could write here C times indicator XS minus is below A. But then having the indicator function there, this means we have a discontinuity in the drift coefficients. And as we've heard, we need somehow smooth coefficients to be able to apply Quasi-Monte Carlo techniques later, or to bound errors in the end. Yeah. Okay, then this type of process fits perfectly in the framework of piecewise deterministic Markov processes. This means we write down the characteristics of this PDMP for our process. We know, okay, we are not in a lack of memory situation, having exponentially distributed interjump times. We are having a renewal type process. This means to end up with a Markov process, we need to Markovize, and add the time component t prime, which is this, it's called backward Markovization, and this means we need to add the time since the last jump. So t is absolute time, the time of the last jump is t and t. And okay, that's just the time which elapsed since the last jump of the counting process. Yeah, for this we know we have some hazard rate for the renewal process, and that's just a fraction of density of the interjump times divided by the tail function. This means the lambda governs the jumps, the jump times. The piecewise behavior is stored in the operator x. This means drift 1 in the time direction, drift c times x in the x direction. And the jump distribution, or the post-jump distribution, is somehow linked to the jump size distribution fy. Okay, and we see that it depends obviously on the position where the process jumps. So that's the x, or jumps from, yeah. And the post-jump location is the x minus the yi for the first jump. And since the yi is iit, this gives us the structure of the jump kernel Q. Okay, putting these things together, we can write down the generator of the process. The A applied to some suitable function f, that's the vector field, or the operator x, describing the deterministic behavior, the hazard rate, times the jump part, yeah. This means the pre-jump location, post-jump location, and what is important here in this situation, we jump at time t prime, and then the t prime gets immediately reset to 0. Yeah, this means that's, yeah, if there is a jump, there is a deterministic shift from t prime to 0. Yeah, this means that the probabilistic, or the non-random, also the random jump happens just in the first component, in the state variable of the reserve. Okay, then since we want to mimic or approximate reflection, we start, or we assume a standard drift c tilde, which we would like to switch off. Yeah, this means that's just a proposal for a concrete choice of the function c. And this means we take the full drift up to a level just below, also below the level of interest A, also just to a minus epsilon. Then we smooth a bit, having from between c tilde and 0, and we can do this, yeah, with a polynomial of order 3, yeah, such that we can also bound the derivatives here. So this would be one choice. Yeah, so this is just a smoothing between level c tilde and 0. Yeah. Okay. And for later usage, we denote the ODE solution, or part of the x component here, so part of this component, by phi tx. Yeah. We can forget about, or we actually do not need to use the t prime component in the deterministic evolution, since we will look at the process just at the jump times. And this means we just look at t prime when it's 0. Okay, then, yeah, these are sample paths of this type of process. As you see, we have the constant c tilde here, and then we start switching off the drift, and the A is chosen to be free. This means the process, as long as it is alive, also as long as it is positive, the process is really kept between 0 and level A. This means we have no restriction on the jumps, also that we have probability mass on R plus for the jump sizes y. This means the process gets ruined with probability 1. Yeah, also at one point there is, also in finite time, there is the probability that the time of ruin is finite is 1 actually here. Yeah, this means if we look at these penalty functions, this means we look at the process, or at the deficit at ruin, that's this quantity. The surplus prior to ruin, this is just, also tau is the first time the process jumps below 0, and this is just the value where it jumps from. Yeah. Okay. If we look at something like this, we do not need the indicator function of the Ruin event to happen in finite time, yeah, because this is an event which happens with probability 1. Yeah. Okay. And now we would like to calculate this function v of x, which is called this discounted penalty function, by means of integration. Yeah. Okay. Yeah, and the w should be continuous and somehow integrable. Okay. Yeah. As we have seen in the general setting for these piecewise deterministic Markov processes, yeah, we try to solve this problem by means of integration. Yeah, this means we exploit the Markov property of this type of PDMP at the jump times. Yeah, then we introduce this transition operator T. This means it acts on a continuous and bounded function, and it's just the expected value of having Ruin at the first jump, paying these penalties, or facing the first jump, restarting the problem. So it's just exploitation of the Markov property at the first jump time. Yeah. Either we continue, then we just rescale the time a bit, restart the problem, and we face the same penalty, and then but with a new starting argument. Yeah, this means the Markov property automatically, and the definition of the function v from before gives us automatically that this expected discounted penalty function is a fixed point of the operator a. Yeah. Okay. And now, yeah, one can show some analytic properties. This means by out of the definition of the function v, we have that it's continuous and bounded. Then we have even for delta equal to 0, we have at least pointwise convergence of the iteration of this operator t. Also, we start with some initial function v, so some bounded continuous function, iterate the operator n, and this converges pointwise to the quantity we would like to compute. And if we have a little bit of discounting, we even get that the t is a contraction with respect to the supremums norm. Yeah, this means in this case we can use Banach's fixed point theorem and get even uniform convergence in the end. Yeah, but we have a bounded domain for the process. Okay, now we look at the operator t in some more detail, and yeah, we just write down what it is. Yeah, we integrate against the density of the jump times, or of the first jump, and then we need to either we need to restart at the post-jump location, and the post-jump location is xt1 minus yi, and the yi has the game size distribution. We are able to restart if the jump is small enough is not causing ruin, or it causes ruin and we stop the problem, but we need to pay the penalty. Yeah, this part with the restarting value v, this is stored in the operator g. Everything else is stored in the operator h, or in the function h actually. Yeah, and the function h means, okay, this is what happens. This is the penalty we pay if the next jump causes ruin. Yeah, and the first time it's the first jump causes ruin. The g pushes the problem forward by one jump time. Yeah, this means if we iterate this one, we survive the first n jumps. This means this gives us the iteration of the n-fold iteration of the g, or we have ruin at the first jump, the second jump, or the n-1 jumps, and this is the g to the power, also k times iterate applying g to the function h. Yeah, because then we have a shift forward in time of this function g. Okay, now we can also iterate the interpretation with the integrals, and then we arrive at an iterated integral of this kind. Yeah, we have k jump times, that's the integrals between 0 and infinity. Then if we apply the operator G k minus 1 times. We have k minus 1 jumps which do not cause ruin. They are stored here. And the k jump which is forced to cause ruin. And this is this one here. Yeah? Then we have the interjump times densities. We have the penalty at the k jump. And we have all possible jump distributions from before. Yeah? This means that's very similar to the integral we've seen in the second talk, but we have much more structure now because we have a more explicit jump kernel. We have a much more explicit interjump times distribution. That's why we have a form for which we can say something later on. Yeah, and okay, the function w just applies in the last two variables, also the k jump time and the k post jump location. Okay, now for being able to apply Quasi-Monte Carlo integration, we need to transform the problem back to the unit cube. Yeah, yeah. Okay, what we need to first transform the jump times. This means that the time of the ith jump is replaced by the logarithm of alpha I. The alpha I is between 0 and 1, also between 0 and 1, negative argument. This means that's the immediate transformation for the interjump times. Okay, the first k minus jumps, they take place between 0 and the pre-jump value. Yeah, this means we can proportionally transform them to 0 to 0 1 with the beta factor, so proportionally. And for the last variable, this realizes between xdk and infinity. We take again the logarithm or an exponential form for the beta k. Okay, but this is straightforward. But we have a nested structure all these alpha i's and beta i's are interconnected because we have a recursive structure in the paths. This means the value prior to the ith jump is a solution of the ODE, which depends on the post jump location from before. The post jump location from before, from the very last jump, that's the ti minus 1, the x. But this is again a solution of an ODE, from the last period, and depending on the last claim size or on the last jump. Okay, this means actually the path up to the ith jump is a function of all predecessor interjump times and all predecessor jump sizes. Yeah, and this means actually that the yi is a function of the first I interjump times and even all of the jumps which happened before. But at least something positive is the type of the Jacobi matrix, because it has lower triangular form. This means that the determinant is given by this expression here. We can put everything back into the integral, and then we get this form of integrand, and we integrate now in the unit cube, in the 2k dimensional unit cube. Okay, and now also the recursive structure is a little bit hidden. That's in the xti, also xt1 up to xtk. But this is the form. And now, if we would like to apply this concept of k variation, which we've also seen in the second talk, then we need to bound somehow the L2 norm of this integrand here. Because then we are able to give an error bound on the integration error if we approximate this integral by the Quasi-Monte Carlo method. So by just choosing a number of deterministically chosen points, and then the error is given by this Cox-Malavka type inequality, but now the k variation times the isotropic discrepancy. Okay, let's have a look at this integrand here. We need to bound some operator norm. This means we bound the 2 norm, and actually we just look at bounds on the squares of the entries of the Hessian matrix. And what we see is, if we take derivatives of this integrand with respect to alpha I and beta j, or alpha I and alpha j, we have some nested structure, or the nested structure of the path strikes back. Yeah, this means we need to have derivatives of the ODE solutions, or of the ODE curves, with respect to initial value and with respect to time. Yeah, with respect to time, this is clearly the drift function C, and then we have this type of I think it's variational equations for the sensitivities of ODE solutions. Yeah, and now it's clear, if we exploit some classical arguments, we get that the first derivative with respect to the initial value can be written in this form. Yeah, and now it's clear that we need to have bounds on the derivatives of the drift function C prime, because we need to control all the possible first and second order derivatives of the ODEs, or with respect to initial value and also with respect to time. So that's why we need to bound this. And yeah, at the same time, if we take derivatives with respect to the alphas or the y's or the betas, we also get obviously terms which depend on the probabilistic ingredients. Yeah, the density of the interjump times and the density of, if you assume a density of the jumps of the jump distribution. Okay, but if we take a particular choice, for example, also which works out is if we choose gamma distributed intercame times and gamma distributed jumps, then we manage to show that we can bound this integrand, and under the conditions on the drift, which we've seen, also bound the derivatives of the C, a smooth W, and what is really strange, or we get some additional integrability conditions on the probabilistic ingredients. Yeah, this means, yeah, but it's somehow natural, because we need to bound the derivatives of the integrator, but this can be linked to expected values somehow. In particular, the integrand evaluated at 0, but this means that in the original time this happens at infinity, and we need to control this behavior. This means we get integrability assumptions or strange integrability assumptions on the probabilistic ingredients. Okay, and here's some numerical example, some toy example for which there is an explicit solution available, but without smooth drift. Yeah, the correct solution is the red line. And then we compared a little bit. So the green dots are direct Monte Carlo simulations. Then Holton sequence, that's the crosses, and blue dots, that's application of the Sobol sequence. Yeah. Okay. Yeah, the methods work, but that's somehow the red value needs to be different to the other values, because that's the non-smooth problem. Yeah, but it's just to have some orientation. Yeah, okay, but what do we see? That's the error to the red line. In the end, the Monte Carlo, so all converge more or less to the same value. This is fine, and there should be some distance because of the smoothing. Yeah, and that was just an toy example if everything works out. Yeah. Okay, then how much time do I still have? Okay. 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 Then, yeah, just to sum up a little bit the first problem. Okay, we found some application where we could explicitly bound the K variation. Yeah. This was mainly done using Mathematica, because for somehow optimizing the view on the integrand, or the derivatives on the integrand, or get some structure there, there was massive need for some symbolic computation in the end. Yeah, but then one could see that the integrand here, or the derivatives of this integrand, as function of the inner derivatives of the ODE solutions and the parameters, that's somehow a polynomial, yeah, and because or a polynomial in the end, yeah, and there was need to bound this polynomial in terms of these sensitivities, and yeah, it worked out, yeah. It should also carry over to other type of distributions, yeah. Yeah. What is maybe a point for improvements is the type of transformation, yeah. Also, I heavily believe that there are better ways to transform our integration domain to the unit cube for not getting into trouble with, or for not ending up with these additional integrability conditions, yeah, because they mainly come up because we have this proportional transformation which causes the 1 over x terms in the determinantor. Yeah, and this gives also this asks for integrability conditions in the densities of the y and the w's. Yeah, so this may be a point. Yeah, to bound the Hardy-Krause variation of this type of integrand seems to be hopeless. Yeah, it may be possible, but we didn't see a chance there. That's why we were very happy to see the results from Bausinger and Swane, where they introduced this K variation. Yeah? But actually for C2 functions, this was always I think already present in the paper by Zaremba in the 70s. Yeah. Okay, then let's have a look at this another application. Yeah, but at this point, this is more or less left out for future research, because at the moment we just use direct Monte Carlo simulations, and the ideas we need some help solving stochastic optimization problems. Yeah. Okay, the ideas was already mentioned, I think, in the first talk. We look at our surplus process X. The basis is this now the classical risk process, the NT is a Poisson process, but we modify or are able to control the jump size distribution. Yeah, and in this case, in insurance applications, means this R is some sort of reinsurance contract. Yeah, and the starting point is we have some parameterized family of reinsurance contracts, and we are able to choose between different types of contracts over time. We pay premiums according to our choice of the contract. This means the C becomes non-constant, and we pay the claim or the remaining claim depending on the choice of the contract, and that's the function R. The U, that's now a process which takes values in the parameters of the contracts, and the U needs to be a previsible process, yeah, because we should not be able to cheat and choose at the time of the claim occurrence the type of contract, yeah, because then we just ask for full reinsurance here if it's possible and do not pay anything for this type of contract here. Yeah, so previsibility is natural and technically important. And now we are okay, we can control the process, and one goal or one exemplary goal would be to minimize this type of discounted penalty function. Yeah? As again, as before, penalty function depending on surplus prior to ruin and surplus at ruin or deficit at ruin, and we may include the time of ruin. And the goal is to find a minimizing strategy such that we find actually the minimal penalty function. Okay, and now so it's not about solving the problem. The idea is how we need to use Monte Carlo simulations, and we would like to use QMC integration for solving such problems. Yeah. So the first step is, the function is clearly nice enough to apply the dynamic programming approach, and we can link the function V to this sort of that's an integral differential equation with the sup or the inf over all the control parameters. This is called an Hamilton-Jacobi-Bellman equation, and it can be directly shown that the function v is regular enough for being a solution to this type of equation. Yeah. Okay, but the equation or the definition of v doesn't give us an immediate initial value, because if we start in 0, for example, or what can happen? Okay, we start in 0, we could do nothing, then we have some slope out us, then we grow out of 0, and then we go on, because or if we are in 0 and our future expectations are very bad, or the penalty is very severe, this means we could also choose reinsurance or pay more reinsurance than we earn on the premiums. This means we have a negative drift and we destroy the process. Yeah? This means it's not clear if the phi of 0 is W00 or something else. Yeah? This means the initial value of the problem is part of the solution. Yeah? Yeah. What can be shown, because out of the properties of v, the function v is continuous and bounded, and it solves this equation. Yeah, and this means it's almost it's absolutely continuous actually. Yeah, this means it's in the domain of the generator if the u is kept to be constant. Yeah. Okay, but for the uniqueness, we need to fix somehow the initial value. Yeah. Because if you do numerics on this type of equations, one can find negative solutions which are not bounded, solutions which are not monotone enough, solutions which become negative. Yeah, and everything depends on the correct choice of the initial value. And for fixing the initial value, we again look at an operator. Also, before we've looked at this transition operator G, pushing everything one jump time forward, and now we look at the operator G, which does the same actually, but needs to incorporate the control. Yeah, so again the same type of operator. Yeah, continuation or restarting the problem at the first jump time, stopping the problem, paying the penalty, or actually killing yourself by taking negative drift and paying this penalty. Yeah? But this is part of the optimization problem. Again, from the time we have that the function we look for is a fixed point of this operator G. Yeah? And at the same time, we can show that actually each meaningful solution to the equation here, also to this Hamilton-Jacobi-Bellman equation, is a fixed point of the operator. Yeah? Yeah, and now the operator G can be shown to be an contraction. This means out of the properties we get that the V is the unique fixed point of G if G acts on bounded positive and continuous function. Yeah, and important is the correct bound of the initial value, the W00 here. Yeah, but this is just a bound on the initial value and not the correct initial value. And now the task is to somehow compute this function v here, or the function phi. Sorry. Yeah. Okay. This means what is typically done. Yeah. The typical idea is to use some sort of Boris iteration. This means you fix some initial strategy. One computes the discounted penalty out of this strategy. Then locally improves the control. Locally improving control means we plug in here the pre-computed function v and recalculate or find minimizing arguments in the control parameters. Yeah, yeah. This means we get an update of the strategy. We can compute the value of this strategy or the penalty of this according or to this strategy, and so on. Yeah, so the locally minimizing over the parameter space, recomputing, and so on. Yeah. Okay. If we locally minimize, the strategies we face there are obviously just depending on the position of the process xt at time t minus, because it should be previsible. This means we are facing processes with coefficients, also drift coefficients, which depend on the state, and also a jump size distribution which depends on the state. This means we are precisely in the PDMP situation. Yeah, and now the idea is to use for the PDMP situation this type of Feynman-Katz formulas we've seen to compute the V0. Yeah, so they apply if everything is regular enough, but because we lack uniqueness somehow, or we have uniqueness just for the correct growth behavior or correct properties of the solution, if we catch the correct initial value, we cannot just use some finite difference method to solve these equations. We need to catch boundary values. Yeah, and for catching the boundary values, we exploit at the moment Monte Carlo simulations to compute the correct initial values here, then use the integral differential equations to compute the function on a larger domain, improve the U-bound, again simulate the V0 out of the improved strategy, and so on. Yeah, but the simulation can be directly linked to the iteration of the operator G here, if we fix a strategy here. Yeah, so there is it can be cast into the framework of the iterated integrals, as we've seen before, but it's not clear how to get smooth enough coefficients here, depending on the control. Yeah, and the controls typically have discontinuities here. And yeah, for example, also just to show you some results. Yeah, we start with a penalty function of this form. This means we have, as we bound it, artificially bound the value function. Then we have some sort of mixed moment. Yeah, first moment of the surplus prior to ruin, second moment of the deficit at ruin. And what we do is, like, this is what we see here: the blue, the red, the green curves. That's like expected penalties along the iteration, and the dotted curves, that's the associated strategies, and that's what we can call the optimal strategy in the end. Yeah, this is one example, but the iteration is needed. Yeah, and what we've seen, if we do not use the optimal controls, we do not have monotone decreasing solutions. We just know that the optimal one or the minimal one is decreasing. Yeah, and in each of the steps for the strategies U2, U3, U4, U6, and so on, we needed to use lots of simulations to fix the initial value. Yeah, if we use a slightly misspecified initial value, we do not get positive. Also, we do not have bounded or positive solutions anymore. Yeah. A too large initial value leads to an explosive solution of the equation, and the too small initial value leads to something which leads to something which becomes negative. Yeah, so we need this V0 by simulations or integration to be able to solve the problem in a meaningful way. Yeah, and this can also be seen here. So that's another application here for Pareto type distributed game amounts. The same function here. Yeah, and that what one sees here is just the y is here exponentially distributed. This means that's a light-tailed game, and here, yeah, if the initial capital is large enough, one allows the process to survive. But here, this type of optimal strategy always needs to negative drift. This means one is destroying the process, but not at full speed all the time. Yeah, that's a nice result for this sort of problem. Yeah, and here again, the iteratively calculated solutions. Yeah, okay, and that's in principle, also in principle, what I wanted to tell you. So we've seen two applications of integration in risk theory. The first one was an example somehow constructed to be able or to get an idea how to bound the K variation for this type of problems. And yeah, one sees a little bit that the smoothing of the coefficients is really necessary. If the smoothing is done correctly, we can still have consistency as like the smoothing parameter epsilon tends to 0, that we approximate the real quantity of interest or of the original underlying model. But the examples we've seen or the problems we've looked at show us or tell us, unfortunately, that the smoothing needs to be done case by case. Yeah, also there is not for each type of, or for a broad class of PDMP type processes, and universal recipe how to smooth the coefficients such that in the end the integral has a finite K variation. Yeah. Okay. Then the PDMP models. Okay, that's somehow future tasks to maybe find something which is more generally applicable, not case by case, and also get an idea for an maybe more efficient method to catch initial or boundary values for the stochastic optimization problems. Because if we fix the boundary values, we can efficiently solve in the rest of the domain by using finite differences or something well established for the integral differential equations within the policy iteration procedure. Yeah? Okay, then yeah, I would like to thank you for your attention.